Hey everybody, welcome to today's video on heat of formation. So, we've looked at physical changes and the enthalpy changes that accompany those. Specifically, we've done some work with enthalpy of solution. Here's a dissolving process. We could also look at the enthalpy change in a process where a liquid simply turns into its vapor. That's a physical change. The enthalpy change involved is called enthalpy of vaporization. And this one is for the melting process where a solid turns into a liquid, enthalpy of fusion or heat of fusion. And we've looked at the enthalpy changes that accompany different reactions, chemical changes. So here's a reaction. Now, if the reaction is specifically a combustion type of reaction, then we denote that delta H as enthalpy of combustion. We're just getting a little more specific here. There is also an enthalpy of reaction for the specific reaction in which 1 mole of compound is formed from its elements. When that is the reaction that you're looking at, the enthalpy change that accompanies it is called a heat of formation, enthalpy of formation. So for instance, if you think about forming a mole of salt, sodium chloride, we know that the elements would be sodium and chlorine, making sodium chloride. Now this guy's not balanced, so I would put a 2 here and a 2 here. That's the balanced equation to take the elements and form sodium chloride. Note, however, that in a formation reaction, we're looking at forming 1 mole of compound from its elements. This equation shows 2 moles. So if I multiply through by 1/2, then I get this equation, and this is a formation reaction. This is the equation for a formation reaction, and if you measured the enthalpy change of this, then that specific kind of enthalpy of reaction is called heat of formation. Okay, so thus far in our study of thermochemistry, we have calculated delta H through calorimetry experiments. That's where we solve for Q and then convert it into kilojoules per mole. We've looked at Hess's law, where you approach it like a puzzle and you find equations that you can add together to get to the equation that you're interested in. The third way that we're going to explore in this unit is using data from these kind of heat of formation reactions. Okay, so I'm going to derive for you the equation that we'll use for this method. So just kind of bear with me here. Let's suppose that we have these 3 equations. We have 3 carbons and 4 hydrogen molecules making propane. That's a reaction. It has this delta H value. But do you see that this is a formation reaction where 1 mole of a compound is formed from its elements? So this value right here of the delta H is actually the heat of formation for propane. Here's a second equation. Carbon and oxygen make CO2 gas. This is also a formation reaction. We're making 1 mole of compound from its elements. The delta H for that reaction has this value, and that delta H is the heat of formation of CO2. Here's the last one, taking the elements hydrogen and oxygen to make 1 mole of water. Here's the heat of reaction, and more specifically, we call it the heat of formation of water. Okay, so let's now see if we can use Hess's law to derive the heat of reaction for this guy. So this is a combustion reaction, and we simply want to know its delta H. Okay, so what we're going to do on this is use our Hess's law strategies and these 3 equations. Let's start with making this product. You see that this middle equation here gives CO2 as a product. So I'm going to use that one, but I want to end up with 3 CO2s. So I'm going to take this equation, I am going to multiply through by 3. And that means that the delta H would be, oops, can you guys see that okay? I multiplied this equation through by 3. That means I would take this number value and multiply it by 3, but I'm going to say simply that I'm going to take 3 of the heat of formation of CO2. Okay, let's look at the next product. 4 waters. My third equation here shows me the delta H for forming water, so I like that one, but I want to multiply through by 4. So I'm going to have 4 H2 plus, okay, 4 times half is 2 O2, and that will make 4 H2O. And the delta H, when I multiply through by 4, would be 4 times this number. But for now, I'm just going to say 4 times the heat of formation of H2O. Okay, so I am using Hess's law. I have achieved the 3 CO2s on the product side, the 4 waters on the product side. Now I want to get this propane on the reactant side. So this equation here gives me propane, but I'm going to need to reverse it. So I'm going to put C3H8 on the reactant side, and I'm going to put 3 carbons and 4 H2s on the product side. And because I reversed the reaction, I want to say over here that my delta H is the reverse of the heat of formation of propane. Okay, now let's see if these 3 equations add up to give me my target equation. And you see that I have 3 carbons on the reactant side and 3 on the product side. I'm going to subtract them out. And I have 4 H2s on the reactant side and 4 H2s on the product side. I'm going to subtract them out. And what I'm left with on the reactant side is C3H8 plus 5 O2s to produce 3 CO2 and 4 H2O. And sure enough, the sum of these 3 pieces is my target equation. So the enthalpy of formation, the enthalpy of reaction, the delta H for this guy, is going to be the sum of these. Okay, so what I'm saying is the delta H for this reaction is equal to 3 times the heat of formation of CO2 plus 4 times the heat of formation of water minus the heat of formation of propane. Okay, now that translates to this more general form. If I want to calculate the heat of reaction for any kind of reaction, I can do it using heat of formation data. And guys, heat of formation data is tabulated in reference books. In your textbook, on these pages, you have all the heats of formations of many, many, many common substances that we come across in chemistry. So this equation says one way to calculate enthalpy of reaction is to sum up. This capital Greek letter sigma means add them up. Sum together the moles of the heats of formations of your products. Look what I did here. I did the heat of formation of this product. Oh, how many moles of it? 3. And I added the heat of formation of this other product. Oh, there's 4 of them. I multiplied that by 4. Then the equation says, now subtract the sum of all the moles of the heat of formation of the reactants. Going back to this guy, here were my 2 reactants. Now, see how I had here in this long derivation, I subtracted the heat of formation of the propane. But what about the 5 moles of oxygen? How come it didn't show up in this derivation? Well, here's the deal. Can you have a heat of formation of an element? Can you write an equation for a reaction in which 1 mole of an element is formed from its elements? The answer is no. So anytime you are using this equation, if your balanced equation has as either a product or reactant an element, just know that elements have a heat of formation of 0. Okay, just plain old 0. Okay, let's look at one example here. So grab your textbook and look in the index in the back. There's several pages that contain enthalpy of formation values, and we're going to use those to calculate the standard enthalpy of reaction. That's the simply the delta H of reaction. Standard means using standard conditions. All right, so here is our equation. 4 moles of ammonia gas plus oxygen gas yields 2 moles of N2H4 gas and 2 moles of water liquid. I want to know the enthalpy of reaction for that process. Using this equation, I'm going to focus first of all on products. So my products are these 2. I'm going to go to my index in the back of the book, and I'm going to look up the heat of formation for N2H4, and I'm going to look up the heat of formation of H2O. Now, your table will list H2O liquid and H2O gas, and they each have their own heat of formation values. So make sure you're finding the right one. Okay, so again, this equation has me focusing on products first. Here are my products. So I'm going to take 2, because of this, 2 times the heat of formation value of N2H4. Okay, this positive value is given in that table that I referenced before. And remember, we're summing up. I'm going to add to that the other product, which is H2O liquid, 2 of that. So this is the value I find in the back of the book. and I'm going to multiply it by 2. Now, I'm going to add those together, this number and this number. My equation tells me after I've dealt with the products, I'm going to subtract the sum of the heat of formations of the reactants. These are my reactants, so they get considered next. My first reactant is ammonia gas. I find that in my table in the back of the book. It has this value, and I multiply that by 4 because of this. Okay, I am summing up all of the reactants. The second reactant is oxygen gas, 1 mole of it, and that value is 0. Again, guys, remember that elements do not have a heat of formation value. So if you have one of those in your equation, you plug in 0. All right, so let's add up everything here on the reactant side. So here's 4 times the value for ammonia and the 0 for oxygen. Okay, so again, this is the sum of the heats of formations of my products, and I will subtract the sum of the heats of formations of the reactants. So it cleans up to look like this. And then I take negative 380.86 minus negative 184.76. And my final answer is negative 196.1 kilojoules per mole reaction. That is the heat of reaction, the enthalpy of reaction for this equation. Solved not by doing a calorimetry experiment and not by using Hess's law, but simply by using heat of formation data that's tabulated in the back of your book. All right, so these problems are really straightforward. It really is plug and chug. The things to watch out for are losing track of your negatives, and another really common mistake is that people want to jump right in and do these guys first and then subtract these guys, when in fact the equation says take the products first and then subtract from that the reactants, which would be these guys. See how I crisscrossed the arrows there? All right, guys, we'll do lots of practice with those. Hope that was helpful.